Hello, I'm Diego,
I'm Tyler.
and this is our lab report number 7, which is the Michelson Interferometer Part 2. Our TA name is state-of-the-art. Let's get started. So this is the outline of the experiment. In Part A, we did the interferometer calibration. In Part B, we measured the wavelength of the three different light sources. In Part C, we measured the wavelength separation of a sodium double. So here's our setup for the first experiment. We got 2 mirrors, 1 beam splitter, laser source, Heaney, and 1 micrometer.
So some of the setups and theory of part A is that the micrometer is not always exactly accurate, so we need to find a configuration factor to convert between the stated measurements and the actual measurements. By measuring a laser with a known wavelength and looking at the fringes, we can determine this configuration factor. By measuring more fringes, the error is reduced. So for part A, here was the math that we got, and we ended up getting a configuration factor of 13.27. So from these measurements 10.578 to 10.998, the source image moved 100 wavelengths, or 100 fringes collapsed.
So this is for part B. By knowing the configuration factor, we can solve the equation for wavelength, and by counting fringes in the given region for different sources, we can find the wavelength. We need a large amount of fringes to minimize the error, as Tyler said before. So this is Tyler doing the experiment. So he was counting the number of fringes by moving the micrometer, which was moving the mirror directly.
This is the same setup with the sodium lamp and the HENE laser. And then for part B, the data that we got, the laser was 601.5 nanometers, the mercury lamp was 506 nanometers, and the sodium was 563 nanometers. While these measurements all had errors, the errors were consistent, that we were getting shorter wavelengths than the actuals, suggesting there was some persistent error in our setup.
So this is the setup for part C with a diffuse lights and the same mirror and the same beam splitter.
So for part C, the sodium source has 2 distinct wavelengths that are close together but not exactly the same, and their overlap produces some instances of spots with no fringes on the micrometer, also known as nulls. We can find the separation of the 2 wavelengths by locating these spots. So for part C, these are our spots, and then we took the averages of the distances between them, and then by plugging this into the formula of lambda squared over the distance between the spots average, we ended up getting our separation between the wavelengths. We got a number of 0.48 nanometers compared to the theoretical of 0.6 nanometers. This ended up being a 20% error, which, considering the setup, does prove that theory to be pretty accurate.
Thank you for watching the video. Bye-bye.